Hello everyone, my name is Jelena Novak. I'm coming from University of Udine and today I will present work on modeling the cyclic plasticity behavior of chromium molybdenum steel with an isotropic model calibrated on the whole shape of the evolution curve. This work is done in collaboration between University of Udine, University of Rijeka and University of Ferrara. As we already know, a durability analysis of a mechanical components requires an accurate finite element simulation. A crucial aspect in finite element modeling of components undergoing low cycle fatigue is the choice of an appropriate elastoplastic material model. It is important to emphasize that the adopted cyclic plasticity model should follow as closely as possible the material behavior observed during experimental testing. In this work, focus is on isotropic material models. The ability of a plasticity models to accurately represent the material behavior plays an important role in numerical simulations and obviously could have a direct influence on the accuracy of results. So, what we should do when the generally adopted material model is not able to capture the trend observed by the experimental data? A possible solution is to try to test a new model. The aim of this work is to apply recently developed three-parameter model to replicate better the softening evolution of the chromium molybdenum steel. Over the last few decades, several plasticity theories have been developed with the aim to replicate more precisely a material behavior observed during experimental testing. We can distinguish kinematic and isotropic models. Kinematic model assumes that the yield surface translates in the stress space at the same time maintaining a constant size. Here are presented only some of material models, while in the literature we can find many more. On the other hand, isotropic models assume that the center of the yield surface remains at the origin and it expands homothetically in size as plastic strain develops. Also in isotropic model, we can distinguish linear and nonlinear models. Combining the kinematic model with the isotropic model allows us to capture simultaneously monotonic hardening and Bauschner effect with the kinematic model and cyclic hardening or softening material behavior with the isotropic model. As I already said, focus of this work is on the nonlinear isotropic model. Low cycle fatigue tests of the chromium molybdenum steel were performed. The steel was subjected to the heat treatment process, quenching and tempering to provide a specific hardness. 296 HV, 420 and 546. Tests were performed under strain-controlled loading conditions at different strain amplitudes, as we can see from the table. From the table, we can see also that the static parameter yield stress vary for each hardness level, and therefore we can consider data obtained for each hardness level as a different material. Calibration of material parameters for the Chauboche and Voce isotropic model was presented in Bassan et al. Published in 2017. Let's consider first only the kinematic material model and experimental data obtained for 420 HV and 1.2 strain amplitude. Black line presents experimental stress strain curve, while the red line presents curve calculated with the parameters estimated for the Chauboche model. Here are presented only first two cycles. As can be seen from comparison, a good agreement is obtained between experimental and simulated curves. Similar fitting was also obtained for other hardness level and strain amplitudes. Voce's isotropic model is expressed with the presented equation, which require to estimate two material parameters: R infinite, which defines the amount of the saturated stress, and parameter B, which defines the speed of stabilization. R infinite can be determined as a difference between the maximum stress in the stabilized cycle, which is conventionally taken at half the number of cycles to failure for material that never stabilize, like in this case, and the difference between the maximum stress in the first cycle. Parameter R infinite can be positive, capturing the cyclic hardening material behavior, or negative, like in this case, capturing cyclic softening material behavior. Second parameter, speed of stabilization B, can be calibrated with the presented equation. Figure presents on the vertical axis evolution of air over saturated stress, while horizontal axis presents the accumulated plastic strain. Black symbol present experimental data for the chromium molybdenum steel with 420 HV and 0.9 strain amplitude, while the red line presents curve fitted with the Voce model. As we can see, a satisfactory correlation is obtained particularly at the smallest and the largest values of the accumulated plastic strain, in other words, for the first and saturated cycle. Other than that, the model follows a trend that deviates significantly from the trend followed by the experimental data. We can see from the figures that a similar inconsistency was also observed for other strain amplitudes in case of 420, 296, and 546 HB. A similar problem was detected also by Goodall investigating behavior of stainless steel, then Zahal for nickel-based superalloy, and also by us, me and my colleague, during calibration of material parameters for copper-silver alloy. Similarly, like in the case of the chromium molybdenum, the Voce model was able to fit precisely the behavior of material for the first and stabilized cycle. Other than that, the model follows a trend that deviates significantly the trend observed by the experimental data. With the aim to improve the fitting accuracy, we modify the evolution of air in a new isotropic model. Let's say now a few words about the proposed so-called three-parameter isotropic model. Three-parameter isotropic model is described with the following equation, in which R infinite has the same meaning like in the Voce model, and here we have additional two parameters, A and S, that control the rate of cyclic hardening or softening. The proposed expression has a physical basis, being it able to capture the two limiting cases. R equal to 0 for accumulated plastic strain going to 0, and R equal to R infinite when accumulated plastic strain tends to infinite. Sensitivity analysis will help us to clarify better the physical meaning of each parameter. Let's consider now first the Voce model. By increasing values of parameter B, which defines the speed of stabilization, the curve shifts to the left, while its S-shape remains essentially unaffected. In other words, a material with a higher value of B reaches its stabilized condition at a lower value of the accumulated plastic strain. Now let's consider three-parameter model. Increasing value of A parameter and keeping S parameter constant, the speed of stabilization diminishes. The curve shifts to the right. In other words, a bigger amount of the accumulated plastic strain is needed to reach the stabilized condition. By contrast, the exponent S, keeping at the same time A parameter constant, controls the slope of the increasing portion of the curve. In other words, higher value of S give a steeper average slope. The three-parameter model was already tested on copper-silver alloy. As we can observe from comparison presented in the figure, the three-parameter model is able to follow the cyclic softening evolution of the copper-silver alloy from the first to the stabilized cycle. More details about fitting procedure of the Voce and the three-parameter model can be found in a recently published work in Metals. The goal of this work is to apply the three-parameters model on chromium molten steel. Let's consider first experimental data of chromium molten with 420 HV and 0.9 strain amplitude. Black symbols presents experimental data, red line presents curve fitted with the Voce model, and finally, blue line presents fitting obtained with the three-parameter model. For all examined cases, comparison is done also by the use of residual, which provides a local measure of fitting at each point. We can notice that the three-parameter model is able to capture much precisely the cyclic softening evolution of the chromium molten steel than the Voce model. This is even more evident if we watch residuals calculated at each point. Similar results are also obtained in case of the chromium molten steel with 546 HV and 0.9 strain amplitude. What is interesting to observe in this case that the material exhibits around 200 cycles on perturbation. In other words, after 200 cycles, material starts to exhibit the cyclic hardening phenomena for approximately 100 cycles, after which the material starts to again show the cyclic softening behavior. Concluding remarks. The choice of appropriate material model is important to properly simulate the cyclic elastoplastic material behavior, as it affects the reliability of service life estimation. Recently proposed three-parameter isotropic model was applied and verified in the case of the chromium molten steel. Calibration of material properties was done using closed-cycle fatigue experimental data of chromium molten steel with 3 hardness levels and for different strain amplitudes. The three-parameter model is able to capture quite precisely the cyclic softening evolution of chromium molten material. In future, we plan to combine the three-parameter model with the kinematic model, verify the three-parameter model considering also other materials, and implement the model in a FEM code. Thank you for your kind attention.